Okay, hi everyone. Can people hear me? The microphone isn't working, so I'm just going to talk like this. So before we get started, a couple of just logistical items to go over. The first one is end of semester / final project logistics. Usually it is the case in this class that as we get into final projects, people tend to find additional lab time more useful than lecture time. So for that reason, usually once we get into final project season, we'll substitute additional lab time for lecture time. So if people like that idea, then what we'll do is instead of meeting here during the lecture times, I will have the lab open. And those of you that want to can come work for additional hours on your final project. Usually that's what people find most useful. That being said, if there are topics that people want to go over into final project season, if there are certain special topics you want to cover, we can do that. But I just want to make you aware that usually that's what we do. And that transition would probably occur sometime next week or so. So right now we're meeting for about 3 hours a week in lecture, and I would open up the lab for at least 3 additional hours every week for people to come work on projects. People like that idea? I like that idea. Okay. So that's what we'll tentatively do. And we'll do that transition whenever it kind of feels right. For as long as there continue to be questions about lab 3, obviously we'll continue to meet. And then perhaps into final projects as people are working on the same sorts of things, we'll continue to meet, but then we'll just do more lab time and spend more time in there. So what I want to do today is, a few lectures ago, we started discussion of PID controllers, and then it got sort of interrupted by some more pressing lab 3 things. So I want to just kind of restart our discussion of PID control and get as far as we did before, and then finish this discussion. And as I mentioned last time, I'm going to present the PID controllers in 2 ways. The first way, the way that I'm going to present today, is largely qualitative, which is to say, treat it as sort of a, if you see this behavior, this is what's happening kind of explanation. And then on Wednesday, we'll get a little more analytical and try to substantiate some of that qualitative stuff with some more quantitative analysis, looking at Bode plots and differential equations and that kind of thing. But today's going to be a little bit more, I don't know, visceral or something, gut stuff. So interrupting at any time, I'm going to move a little bit more quickly through the beginning stuff just because we have seen it before. But I'll remind you again, none of you need reminding at this point. The system we're controlling is a lever arm with a drone motor at the end that can pivot about a low torque potentiometer. And as many of you have discovered, right, now that you're driving this system open loop, is many of you discovered that this is a hard system to control. And the way that a lot of you have discovered this is you've implemented some mechanism where you can increase the duty cycle to the motor, so you can increase its speed and increase its speed. And what many of you find is you can, by hand, push it up quite easily to about horizontal. And then as you move it past horizontal, boy, is it easy to just flip it over, right? A lot of you have come to discover this, and this is for a couple reasons. One of those reasons is the thrust out of the motor is proportional to the square of the voltage. So you apply a little bit more voltage to the motor, you increase your duty cycle a little bit, you get a lot more thrust. This is compounded by the fact that as we move above the horizontal, the amount of torque required to hold the arm steady is decreasing, right? And in the limit where you're perfectly straight up and down, there's no torque at all. It's just balance. You don't need to have the motor on in order to hold it in place. So as you get higher, your system gets more and more sensitive to your motor control, and it gets harder to control. So I'm asking you to control it to angles up to, at most, 30 degrees off the horizontal. Some of you will get a lot higher than that. Some of you won't. But you're being asked to control it up to at least 30 degrees above. And in particular, at boot up, you're asked to have this arm swing from hanging straight down up to horizontal, plus 30, minus 30 horizontal. And then the user should be able to enter any angle. So as we talked about last time, the one way that you might consider controlling the system is open loop, which is what a lot of you did last week, and what a lot of you are also still working on this week. Open loop control being, we experimentally determine which applied voltages are associated with which angles, right? If we apply 0 volts to the motor, 0% duty cycle, it hangs straight down. If we apply 50%, what's the angle associated with that? And then how does it map in between? And we would generate something like a lookup table where if the user says go to 90 degrees, because we've calibrated our system, we can look up the voltage associated with 90 degrees and send the motor to that angle. But as we've talked about, for some systems, this makes sense. If you're in a highly controlled environment where the environment is unchanging and the system is extremely it's built in such a way that its properties aren't going to change over time, then perhaps something like open loop control makes sense. You might see this in some industrial applications, for example. However, it doesn't work well for our example because, well, our propellers, our little motors are cheap, right? And their properties are highly variable. They're variable between motors. They're variable even within the same motor, right? Their properties are going to change over time as you run them. So if you were to implement something like this, you would first of all find that if you change the environment, you would have error. If you took your arm to Colorado, you would have steady state error in the negative direction because there's less atmospheric density. So you'd be generating less lift. You wouldn't be calibrated for that environment, right? So the system it would work, but with a lot of error. Furthermore, as the properties of the motors changed as you ran them, as they got hotter, you would find that you accumulated steady state error. If you bumped the little motor, you would find that you accumulated steady state error. And for us, that's unacceptable, right? So we have to close the loop here. So that's what we're going to do. And we talked about the problems associated with open loop. In our system, there's a number of them. So what we're going to do is close the loop, which is we are going to modify the control input to the motor based on the sensed state of the arm. So we're going to tell the system where we would like for it to be. We'll use a sensor to determine where the system is. We'll look at the difference between where we want to be and where we are, and use that to calculate an updated command to the motor. This is what the controller does. It takes an error and converts it into a control input. In particular, and there's a whole, like I've said before, you can do a PhD in this, and lots of people do because there's a lot to controllers. There's a lot of options, and different ones apply to different situations. The particular kind of controller that we're going to be implementing is a PID controller, proportional integral derivative. We're doing that for a couple reasons. One is they are relatively simple as compared to a lot of other controllers. So for a 3-week project, this is a good one. The other very good reason to do this is they're everywhere. They're by far the most ubiquitous kind of controller that we see. So it's a good one to learn. So I want to spend the remainder of today talking through these controllers qualitatively, kind of waving my hands at stuff. And the way that I want to do this is,
So it's kind of a general question about can you test whether or not your parameters are tuned to the proper values without having to set up in front of you? Is there a way to do it just by looking at the parameters?
So the question is, can you tune your PID controller without having the system in front of you? The answer is yes, kind of. And one way that you can do that is with a simulation, right? So, and in the lab write-up, we've provided a Python simulation of the pendulum that's pretty good. It's okay. So you could use that simulation to come up with control parameters that you think are pretty close, at least according to the simulation. Use those as a starting point on your actual system, and then modify slightly according to the differences between the simulation and the actual system. But you at very least need a simulation.
So you still potentially need a lookup table when converting ADC values to angles. Is that correct? So
as we're going to talk about, the unit of angle that I recommend you use for this is ADC units. I recommend that you don't, you're going to do some sort of a unit conversion because the user is going to enter the desired angle either in radians or probably degrees. I recommend that you take that user input, convert it to ADC units, and do all the control in ADC units.
Yeah, so is that portion still prone to environmental changes? If you kind of bump your potentiometer, it's not exactly going to be 0. Like if you say 0 degrees, it won't be exactly 0 degrees.
Yeah, I mean, with a,
slippage from the,
it certainly could. When you're talking about a sensor in general, something like a potentiometer, you are worried about a bias, right, which you would have to calibrate out, and then noise on the sensor, which normally you would characterize. So you'd run the sensor for a while and generate a characteristic noise distribution. Usually people approximate it as Gaussian for a lot of sensors, because usually that's a good approximation. And then based on the amount of noise in that sensor, you would make a decision about how that's going to be built, how that noise will, how you will accommodate for that noise in your controller. And in extreme circumstances, or even not so extreme circumstances, you might do something like implement an estimator in addition to the controller. An estimator being something that takes noisy sensor input in and gives you the best possible estimate for your state, whatever your state means for your particular system based on that noisy input. And then that output of the estimator would be fed back to the controller instead of the sensor information directly. Did that answer your question? Okay.
yeah, that was perfect.
So the idea though is that that error would be way smaller than like that wouldn't like vary to the Colorado, right?
Yeah,
It would be like on the order of 1.
Okay.
In estimation, when you're talking about noise, suppose you're making something like an estimate, a common estimator, something like a Kalman filter or an extended Kalman filter, where you have measurement noise being the assumed white noise associated with the sensor, and then process noise, which is the noise associated with the physics of the system. So measurement noise you would get by probably either reading the data sheet for the sensor or testing the sensor. Process noise is a lot more difficult to understand. That's stuff like turbulence. That's just like randomness in the environment. That's very difficult to characterize, but you make some reasonable guesses about it. Other questions? We could do a lecture about estimation if people want. I don't know if that's useful or not, but we can certainly do that. Okay, so as the name suggests, PID controllers, proportional integral derivative controllers, have three terms in them, and those three terms are summed. The first term is proportional to the instantaneous error, which is to say the difference between where your, in our particular case, your measured angle and your desired angle. You look at that difference, you scale it, that becomes that term of the control input. The integral term is, it sums the error over time. So it looks at the instantaneous error at this particular time step, plus the error at the previous time step, plus the error at the previous time step, and on and on and on, right? So that if there's some small amount of constant error, that small amount of error is summed over time so that it becomes a larger contribution to the control input to move the motor up or down to get rid of that steady state error. We'll look at the examples of this. Derivative control looks at the rate of change of the error. So this, it protects you from the situation where we're hanging straight down and we command 90 degrees. The controller sees this huge error, slams the motor on, and starts screaming up towards the desired angle. Without derivative control, what you can expect is to blow right by your desired angle and start oscillating. With derivative control, it sees that the rate of change of the error is very large and very negative, and it will slow the motor down. So it fights back against the proportional control to limit overshoot and reduce oscillation. You see examples of this as well. So one way to think about this is proportional control gives the controller information about the error right now, this particular time step. Integral control gives it information about the past error. And derivative control allows for it to make guesses about the future error. So the proportional control will say the error right now is huge, so I'm going to turn the motor on high. Integral control says we've had a little bit of error for a long time, so I'm going to speed the motor up. Derivative control says I see the error going down fast. We're going to overshoot. I'm going to slow the motor down. We'll look at each of these independently. So let's start with the proportional term, which, by the way, is the one that I recommend you start with. Okay, well, I'm going to sort of talk through the recommended development process here as well. So the proportional term, in order to implement only a proportional controller, what you will do is enter the interrupt service routine, take an ADC measurement from the potentiometer. That tells you where you are, tells you where the arm is. You'll compare that to the desired, the ADC measurement that you would get if you were at the desired angle, right? That's going to give you some error measurement. One minus the other is an error. You're going to scale that, which is to say multiply it by some constant, which we'll call K sub P. You'll hear this called the proportional gain. Gain being the constant by which we multiply these things. So we'll just take that error, scale it. That becomes our duty cycle. So you think about this and okay, that means if the error is big, then the duty cycle is big, which means if we're down here and we want to be here, the motor turns on fast. If the error is small, then the motor turns on not as fast. And what we talked about last time is this is a step in the right direction. So this is what this sort of looks like schematically. If this is our error over time, then at this moment, our command and duty cycle will be proportional to that green vertical line, and then it will be proportional to that smaller red vertical line. This can lead to two problems. The first problem is, suppose that at boot up, we were holding the motor precisely at 90 degrees, precisely level, and we only had proportional control. And then we turned the system on and we said, go to 90 degrees. It would see exactly zero error, right? Because it would measure its current angle and say, oh, 90 degrees. And then it would look at the desired angle, say 90 degrees, the difference is zero. So we would scale zero, that would become our control input, and the motor wouldn't turn. And then when we let go, as the error started to increase, the motor would spin faster, right? It would start to come back up towards where it wanted to be. But as it approaches the desired angle, the error is dropping, which means the command input to the motor is decreasing, which means it's slowing down. So as you get closer to the desired angle with just proportional control, the motor's slowing down. And at some point, the torque from the motor matches the torque from gravity, and it just stops. And you have some inescapable steady state error associated with just proportional control. If your proportional gain is quite small, that steady state error will be quite large. So here's what a quite large steady state error would look like. So it turns on, we command it to 90 degrees, and it kind of pathetically just bloops up like this, right? So we could reduce that steady state error by increasing the amount of proportional gain, right? But then that introduces the second problem, which we suggested at least last time, which is you turn that up too high, then even as we're approaching the desired angle, the command input to the motor stays really large until we're really close to the desired angle, which means that by the time the motor finally slows down or turns off, we have enough inertia built up to just blow by where we want to be. And then the same thing happens in the other direction, and then we oscillate. So here's what this would look like. Some of you got this going last week. So with just proportional control, what you'll find is if you start with the proportional gain quite low, and you command, say, hover at horizontally, you'll see it come up and oscillate and then stop. You'll make it a little higher, it comes up and oscillates and then stops. You'll make it a little higher, and at some point you'll find the gain, the KP value, at which it comes up and starts to bounce and stays bouncing. And when you get to that point, you found the edge of stability for the system. This is how I recommend you start building the controller. Start with just proportional control. Start with the proportional gain, KP, small. Turn it on enough that you get a huge steady state error. Turn it up more and more and more until you see it start to oscillate. And then you're going to add in derivative control, which we'll talk about in a moment. But that'll be the next term that you add is the D part of the PID controller. It's not the next one I'm going to talk about. It should be, but I organized this incorrectly. So let's say we wanted to eliminate the first of those problems, which is to say that steady state error, right? We had a small KP value. We had this steady state error. The way that we eliminate that is with this integral term. which, unlike the proportional term, which scales just the instantaneous error, the integral term sums or scales the sum of the error over time. So that if there is some steady state error, so this is, you'll remember that for the proportional graph, we were just looking at instantaneous errors. The integral graph is looking at the integral, the area under the error curve with time and scaling that. Positive error, positively adding to that summing error term, negative error subtracting from it. So if we add this integral term, so here's a very small KP value. So you'll see that it will, the proportional part very quickly brings the arm up a little bit, and then it has steady state error. And then slowly the integral part sums up over time and increases the control of the motor, pulling it up to the commanded 90 degrees. This is what that looks like. So it's getting pulled up and up and up. And on the VGA in the back, you can see it approaching the commanded hover angle. And if we bump it, it'll oscillate pretty substantially, but then it will damp out and go back to the desired angle. So this would be a PI controller, just the proportional and the integral part of the PID controller, which, as you can see, gets you to the desired angle. But the problem is it gets you there slowly, right? It kind of weakly approaches the desired angle and then stays there. And that's not what we want. We want our system to be fast and responsive. So we want it to snap up the desired angle. And then when you command a new one, it very quickly snaps to the new one. You'll be evaluated in part on how quickly your controller is able to move this thing. Yeah.
Will that be like the faster you snap? Is that proportional gain instead?
Yeah. So this ends up being, you have combating forces here. So the higher you turn up the proportional gain, the faster the response. But the faster the response, the greater the potential overshoot and the longer the ringing, right? So you're trying to balance speed with overshoot and settling time. This is one of those things, by the way, that when you first, when you're working on control problems, you're not, this was bothersome at first to me because it's not a problem necessarily where you're trying to find right answers. There's not necessarily a correct proportional, integral, and derivative gain value. What you have instead are requirements. For problems like this, those requirements are usually how much overshoot are you willing to tolerate? What is the minimum rise time you're willing to tolerate? How long of a settling time are you willing to tolerate? And then you find control values that meet those requirements. And there may be lots and lots and lots of potential control values, all of which meet your requirements, and none of which are any better than any of the other ones, right? This is a requirements meeting problem as opposed to a specific set of right answers problem, which is just a little different than perhaps other sorts of problems that you've worked on. Okay. So then the last term of the PID controller is the D part, the derivative part, which, as the name suggests, looks at the rate of change of the error, the derivative of the error. So if we look at this sort of plot that we've been looking at here, if this is our error with time, the derivative term is looking at and scaling the slope of this plot. So you can see here that as the error is decreasing quite quickly, the derivative is large and negative. So that becomes a negative contribution to our controller, which slows the motor down as opposed to speeding it up. It fights back against the proportional controller. So what this will do sort of phenomenologically is slow you down as you get to the goal. If this is up too high, if you have this knob turned too high, it'll slow you down a lot. It'll really slow your system down because it doesn't let you decrease error very quickly at all. If this is too low, you overshoot a lot. If you get this tuned just right, it'll really quickly approach the desired angle, overshoot a little bit, you can trade rise time for overshoot here. Maybe you want a faster system that overshoots more, or a slightly slower system that overshoots less. I'm asking you to aim for critical damping here, which is overshoot of, you want the system to overshoot and settle in about half a cycle time. Something like that. We'll look at plots of it. But in any case, this solves that second problem for us, that problem of the bouncing. So what you can see here is, I'm going to show you two videos. One is an untuned PID controller. So a PID controller that has proportional, integral, and derivative parts to it, but not much thought has been put into getting those tuned right to get performance out of the system. So what you'll see is a lot of overshoot, a lot of bouncing, and a lot of overshoot and bouncing for every commanded angle. So it gets to where it needs to go, but not very elegantly, right? And sometimes rise time for overshoot is an okay trade. Sometimes you cannot accept any overshoot at all. So suppose, for example, you're trying to land a rocket on a boat. You definitely don't want to overshoot that boat, right? Because the rocket will explode. In other situations, you're okay with some overshoot. So it all depends on the application. Here's a slightly more, many of you will tune this better than I'm about to show you, but this is a slightly more tuned PID controller. And what you'll see is snappiness without too much overshoot and without too much ringing. So it's hard to see in the back, but you can sort of, there's a little bit of overshoot. But overall, it's pretty quick. This is approximately the behavior that you're aiming for. Questions about this so far? There are a few things that you have to be careful of with implementation that I'm going to talk about next. Yeah.
So the two videos that, those two videos, the code is unchanged besides the values.
The only thing that has changed between the top video and the bottom video is the values of those KP, KI, and KD. Just turning those knobs a little bit.
Pretty impressive.
It's very addicting. Once you get it implemented where you can change the controller values quickly, you will find it deeply addicting to try to get a little bit better performance and a little bit better performance, a lot like Boyd's, right? Other questions? Okay. So there are a few things to be careful about. First thing to be careful about is this issue called integrator windup, where I mentioned that the way the integral part of the PID controller works is you're summing the error over time. Suppose that you put no cap on how big the integral part of your PID controller can get. So that can lead to a situation where you turn on you turn the device on, you say go to 90 degrees, and suppose you just hold it down for a little bit. Then the error is going to stay large for a long time. The proportional part of the PID controller doesn't change, right? Because it's only ever looking at the instantaneous error. So from one time step to the next time step, the P part of the PID controller is the same. It's not growing. The I part, however, if you hold it down for a long time, the error initially at the first time step is large. And then if you keep holding it, it's large again and again and again and again and again. And it can just keep growing. And then when you finally let it go, it only starts to go down once the arm has gotten past its desired hover angle, right? And then you get negative error, which negatively contributes to your adding integral term. And then it'll start to decrease. But at that point, you've blown all the way by your desired angle. So let me just show this video and then I'll get to you. So let me just show you what this looks like. I'm going to show you the same controller without any protection against integrator windup. I'm going to hold the arm down with my foot for like 2 seconds and then let it go. And see, it only slows down after a while, right? Because it has added so much to that integral term. So protecting against, oh, you had a question.
Yeah. What's the two questions?
Yeah.
Was the one the motor like stopped? Was that you stopping it, or was that it slowing down after a while?
That was it slowing down after a while.
Okay. And then to me, it seems like you would want to like zero out or like not take into account the integral term once you've reached a specific angle. So like take into account the integral term and then like disregard all the previous measurements once you've reached that angle, and then so you can snap. Like why?
Yeah.
Why like when like I'm still considering part of the integral term from like an hour ago. I've been running this thing for an hour.
So I agree with you. And the way that I recommend implementing this integral term is rather than sum all of the error since the system booted up,
Yeah.
instead consider summing all of the error for as long as the sign of the error hasn't changed. So if you're down here and the sign is
Yeah.
large and positive, you sum up until it's negative, and then you start a new summation.
Okay.
But when you start that new summation, don't zero the integral term. Because suppose that the P part of your PID controller was weak, so you had steady state error, and the integral part had brought you up to here. Then the integral part is responsible for quite a bit of the control input. If this overshoots a little bit and the sign of the error goes negative and you zero that, it's just going to go boom and then start climbing up again. So what I recommend you do instead is when you detect a sign change in the error, make the integral term something like 90% of what it was, and then start the summation again, which is going to reduce it slightly, and then you start summing again.
Okay. What's that?
You should cap the integral term. You should cap. You should also cap capping the integrator term protects you from integrator windup, right? What I'm suggesting is also not doing the summation infinitely, but only while the sign hasn't changed. And when you detect a sign change, reduce it slightly, and then start the summation again. Now multiplying by 0.9. Uh-oh, that sounds like floating point. Well, or let's see, you could shift by 1. That's multiplying by a half. You could shift by 1 and then add shift by 2. That's 0.75. You keep doing that and get arbitrarily close to 0.9. Do it a few times. Get like 0.82 or something. Yeah.
So like the integral like is say like a negative here, and then you go up a little and you overshoot a little bit, and then it's positive, so it adds like the absolute value, the magnitude, like shouldn't that it goes over, so shouldn't that be responsible for bringing it back down?
Yes. Yes,
So,
it will.
So then why would you want to change it just on like the little side change? Like why would that? I guess like.
That's okay.
Like here, it's like coming up and it's
Yeah.
adding, and then you overshoot a little bit, and you want to come back down, which is why this side change like decreases the magnitude, and then you just calculating. So I guess like what I'm asking, why would you want to change, like multiply by 0.9 or whatever, right when it changes sign? Like I would think you would want to do like that when it steadies out.
Yeah, suppose that you're going past it quite quickly. If your integrator term is too large, you can destabilize the system. So something like what I'm suggesting adds a little bit of stability.
Okay.
Other thoughts about this?
So when you release that, the derivative term should also come into play, right? Then why didn't it try to slow it down? Why it was steering towards the goal?
It did, but the integral term was so big that it couldn't do anything about it. If instead we said the integral term is going to be equal to the minimum between our summed up errors and some maximum value, so that it can't keep just counting up to infinity like shown here, right? We instead cap it somewhere. That then keeps it modest enough that the other terms can actually fight back against it. And if we do something like that, then even holding it down and letting it go, it stays well behaved. Right? There's some overshoot, and if we turn down the max a little bit more, we'd have less overshoot, right? But it prevents it from just exploding.
If you hold it down for long enough, in that case, will it still explode?
No, because it's getting capped. So you could hold it down arbitrarily long and let it go, and it would stay well behaved.
So you're not capping the amount you're adding to each time, you're capping the amount.
Yes, exactly. The other problem we have to be careful about is for the D part of the PID controller, we are taking a derivative. What we have to be really careful here is we don't want to differentiate noise, right? Because that, if you have high frequency noise and you differentiate high frequency noise, you get really high amplitude output out, right? So at best, this can lead to jitter. So you go to, and it starts to jitter. At worst, this totally destabilizes the system. So let me see if I have, this is just a little bit of jitter from not filtering the D part. See it kind of bouncing. At worst, this just blows the whole thing. So how to protect against that? Well, first of all, we build this circuit that all of you have already built, right? We low pass the potentiometer readings to approximately the control frequency. So you all have done this already. The other thing that we do, however, do I have something down here? The other thing that we do is we notice that suppose that the arm were turning as fast as it's ever going to turn. You had the motor on full blast and it was just ripping as fast as it could go. How much would you expect for the ADC units to change from one measurement to the next measurement at 1 kilohertz? So in order to solve this, you would ask, okay, what's the ADC measurement here? What's the ADC measurement here? And how fast can it go from here to here? And then we do a little unit conversion to ADC units and figure out, okay, so how many ADC units do we expect for it to change from one sample to the next? And what you'll find is for a 10-bit ADC, and at the speeds that this arm will go, maybe like 2 units is the fastest that you'll expect for it to change. 2 units on a 10-bit ADC, that's basically just noise. That's just noise. So you have this small derivative signal. So what I recommend doing instead is, if ordinarily, naively, you were calculating the derivative as the difference between your current error and the error in the previous time step, right? And then there would be a delta t here, but we're using time units for delta t is 1. What we do instead is store the error for, I don't know, 4 samples and calculate the derivative as the difference between the error at sample n and the error at sample n minus x, where x is like whatever works really. 4 works well for me, okay? But that's not a rule of thumb. It depends on a lot of things. But you might consider, instead of scaling the difference between error at time stamp n and n minus 1, do n and n minus 4, and that makes that derivative measurement more signal and less noise. Makes sense? Okay.
What's the sum of the error? Or is it just the error?
Just the error at n and n minus 4. Instantaneous error at n, instantaneous error at n minus 4, calculating the difference. Okay. So what should be your initial guesses for these things? And there are systematic ways for coming up with this, which we can talk about. There's also some kind of hand-wavy ways that get you in the neighborhood relatively well. And then once you're in the neighborhood, you play with it. So let's think about, first of all, the proportional gain. And we're going to suppose that the system starts with the arm hanging straight down. you command it to 90 degrees, and suppose you want your proportional gain to be high enough so that for an error that large, the motor turns on full speed, at least for a little while, right? It'll slow down as it approaches, but we want it to respond full speed for that size of error. Then we can get ourselves in the ballpark for what KP might be. Oh, that's a typo. That should be KP instead of KP. So okay. Let's suppose we're running our CPU at 40 megahertz. Those of you that are still overclocked, you're not, right? But suppose that we are. And we're using a 10-bit ADC. Wow, lots of typos. So when we're hanging straight down, we read the ADC. You can experiment with this, but you'll probably find an ADC measurement of something like 250 in ADC units. That's straight down. If you have the potentiometer in the correct orientation, which some of you don't, so just be careful of that. And you'll probably get about 500 when it's horizontal. So that's a difference of about 250 ADC units from here to here. Our PWN, our range of valid control inputs goes from 0, duty cycle of 0. We can't run the motor in reverse. What do we need to run the motor in reverse?
Oh, an H bridge.
An H bridge, yeah. We don't have an H bridge implemented, so we don't run it in reverse. So if our error is negative, motor turns off, right? But so we can provide duty cycle commands in the range of 0 up to 40,000. So if we want the motor on full throttle, when we see an error of 250 ADC units, then that suggests a KP, a proportional gain of about 40,000 over 250, which is something like 160. Something like 160. Something on the order of hundreds, right, is probably what you'll get for KP. Like around that order of magnitude. So maybe you start with like 100 and tune from there. Maybe you start with 100 for your KP value. Okay. How about the derivative term, which, as I mentioned before, this is the next term that I suggest you add, right? So when you're starting to build a controller, start with just derivative, turn it up until you get oscillation, and then add some, what did I just say? Start with proportional, turn it up until you get oscillation, and then add some derivative. So, as I already said, when this is rotating at its fastest rate, the ADC measurements are changing at 2 to 3 ADC units per measurement, right? So, and we're going to take those differences and scale it by the proportional gain or the derivative gain AD. So if we want for the contribution from the derivative part to be non-negligible, which is to say about the same order of magnitude of as the proportional gain, not completely swallowed up by the proportional gain, then we'd like for the product between the derivative measurements and the derivative gain to be about the same as the product between the proportional measurements and the proportional gain. So because these derivative measurements are 2 to 3 orders of magnitude smaller than the proportional measurements, we expect for KD to be 2 or 3 orders of magnitude larger than KP, the proportional gain. Does that make sense? Our error measurements that we're scaling for the proportional part are, on the order of hundreds of ADC units. The derivative terms that we're scaling for our derivative part are on the order of single digit to tens of ADC units, orders of magnitude smaller. So we want to scale it by a couple of order of magnitudes more. So probably your KP is going to be in the range of thousands to 10,000s. Maybe start with 1,000 and tune from there. And if the system is overshooting a lot, you turn it up. That reduces it'll slow the system down. If the system's too slow, turn it down a little bit. So you'll start with proportional. You'll start with proportional until you get this. Then you add derivative, and you'll get this with some steady state error. And then you'll add a smidgen of integral, and that's going to eliminate the steady state error. So let's think about this integral term. Again, we want for its contribution to be non-negligible as compared to the contributions of the other terms. So we want to think about this. The integral term is scaling the sum of the error over time. right? So we're measuring the error, and that error for the proportional term was on the order of hundreds of ADC units, maybe up to 1,000 ADC units. The integral term is summing lots of those. So it is scaling a value that's quite large as compared to the value that the proportional term is scaling, very large as compared to the value that the derivative term is scaling. So we're going to make the gain for this comparatively small. So maybe, probably a good idea to make it a power of 2. Make it a shift, right? Why not? So maybe you start with a value of 1/32 for your integral part and go from there. And if you see a lot of steady state error persisting, turn it up a little bit. So just to summarize, this is how I recommend you go about this. Here's how I recommend you go about this. What is your interrupt service routine going to look like? I've said this a few times, but your code in this lab is very simple. There's a thread or 2 for taking user input, and there's a 1 kilohertz ISR. In that ISR, you're sampling the ADC. You're comparing the ADC measurement to the desired ADC measurement, and taking that difference is interpreted as the error. You then take that error, and that error goes into your PID controller. The P term of the PID controller just scales that by whatever KP is. It'll probably start with 100, right? The I part adds that current error that you've just measured to a variable that's accumulating the sum of those measurements over a period of time and scaling that. The D part is comparing your measured error to the error that you measured 4 or 5 samples ago and scaling that. So that error comes in, calculate the P part, calculate the I part, calculate the D part, add them all up. The output of that is a duty cycle. And you send that duty cycle off to the motor that will change the motor's position, and then you'll interrupt again and do it all again. And it should move you towards your desired angle. You're doing a couple of other things in that ISR, including sending the measured ADC value out to the DAC so that we can look at it on the scope, and also low passing the PWM command and sending that out to the DAC so that on the DAC at the same time we can see the motor state and the control input. I'm going to talk about that low pass filter next time. There's been a little bit of confusion around that, so I'll talk about that next time. In any case, you're going to start with just the proportional part of that PID controller, turn it up until you get oscillation. Then you're going to add derivative gain to suppress that oscillation. And then you're going to add integral gain to eliminate the steady state error. And then you're going to turn the knobs a little bit. And you're going to try to tune the system so that it is as fast as you can make it without overshoot that's extreme and without too much ringing. Okay? Questions about this?
Like when you say some of us will be able to get like better and stuff, does that come from stuff like the 90% multiply, like, you know, just like other little things that we do in our code? Not like technically part of it.
You're not super time constrained in this lab. So in boards, you were crazy time constrained. Even in lab 1, you had pretty substantial time constraints for the computations you were doing. In this one, we're interrupting at 1 kilohertz, which means you have 44,000 cycles to spend. That's plenty. You could probably get away with floating point. Don't, because why? But you probably have time to get away with floating point if you wanted to. So the performance will come more, once you have the controller implemented, you'll get better performance by better tuning those gain parameters.
Yeah, but I'm talking about like, because like, we didn't like in the actual document mention things like that, like, you know, setting it at like 90% of what it was, things like, you know, there's like little things that intuitively make sense. Like, I'm assuming, I don't know how much of that people will actually be able to think of and implement, but like, is that where you get the most significant gains after you put that to, like?
I suppose so. Yeah, I suppose so. Yeah.
Is sampling faster better for us, or is it a moot point after a certain point?
A higher frequency, if you control the motor more quickly, you'll better be able to get it to do what you want it to do, even when it's in a very difficult to control part of a very difficult to control state. However, this motor acts like a low pass filter, right? So if we were sending it different PWM commands at 10 kilohertz instead of 1 kilohertz, it's going to just smooth that out in the same way that it did the 1 kilohertz. So I'm not exactly sure how much benefit you would actually get from that. Something people might experiment with. Yeah. Okay. I'm going to open up the lab today at 3. Anybody wants to drop by, and I'll see the rest of you on Wednesday.
All of the parameters wouldn't really, like, none of the tuning would change if you like took it to the
That's correct.